In our first few lessons on vectors, we learned how to sort of interpret and understand vectors both geometrically and algebraically. What we're going to be doing today is sort of getting into how we can use algebra to solve equations that involve vectors. Before we get started, though, I'd like us to take a deep breath because this is probably still something that's quite new and sort of disorienting for you guys. So let's take that deep breath. And let's begin. I'd like to start with a bit of a warm-up here, just to make sure that we're sort of comfortable with some of the adding and subtracting and scalar multiple vectors that we learned in the previous lessons. So I'd like you to carry out the following vector operations given those two starting vectors that are in column form. And remember that we can either have vectors like this as columns, or we can have them in the IJK notation. For now, I'm just going with columns. So pause the video, make sure that you can do these things. All right, so for a minus b, I just need to do 3, 5, negative 2, and then subtract negative 1, 2, 4. And we recall that when we're adding or subtracting vectors like this, all we're really doing is combining them component-wise. So the x's will go together, the y's will go together, and the z's will go together. So if I do the x's first, 3 minus negative 1 is going to give me 4. The y components, 5 minus 2 will give me 3, and the negative 2 minus 4 will give me negative 6. So yay, there's my answer for that one. Okay. Moving on to the next one, 3a. This is what's called scalar multiplication, because I'm taking a scalar, 3, scalar is just a number, and I'm multiplying my vector 3, 5, negative 2 by that. And remember what this is going to mean geometrically. Like, if you need to pause the video for a second, what is it going to mean, like, geometrically when I multiply this vector by 3? Hopefully you recall that means that we're scaling, we're sort of stretching this vector to be 3 times as long. And to do it numerically, I'm just going to multiply this 3 to each of the components. So my top component is 3 times 3, which is 9. The y component, 3 times 5 is 15. And the z component, 3 times negative 2 is negative 6. Yay, we're done. In the last one of these, we're sort of combining these two skills together, where you're going to do a scalar multiple on A, and then minus a scalar multiple on B. Okay, so for this one, we just need to do 3 times A, which we actually just did in the previous one, and then minus 2 times this one. We already figured out that this one was 9, 15, negative 6. For this one, you might be wondering if you should distribute the negative 2 or distribute the 2. Doesn't really matter. Just keep in mind, if you're going to distribute negative 2, then the operation in between becomes plus, and if you're distributing just 2, then you're going to leave a minus in between. I'm going to go ahead and just leave the minus and distribute the positive 2. So this will give me negative 2, 4, and 8. And now when I subtract these things component-wise, 9 minus negative 2 is 11. 15 minus 4 is actually also 11. And then negative 6 minus 8 gets me negative 14. And there's my answer for that one. So the purpose of this warm-up was just to make sure that you know how to do these little vector operations, that you know how to add and subtract and use scalar multiples of vectors. We're really going to need that for the work that we're doing today. But before we get to that work, I do have one important question. And that important question is, what impact do the y and z components of vectors have on the x components when you're adding, subtracting, or multiplying vectors by a scalar? So pause the video and think about that for a second. What impact did these y and z components have on the result of the x component? And hopefully you realize that had no impact at all, right? The whole idea behind these things is that the x component depends solely on the original x component. The z component depends solely on the original z component. So the y and z components had nothing to do with the x component. That's going to be really important in where we're going next. So now we have this sort of like super duper key point, right? And this is like critical for working with vector algebra. When you are working with or solving a vector equation, you can basically consider a separate equation for each of the components of the vectors. Okay? And I've got a fairly simple example here that I want to use to show you what I mean by that. Okay, so let's go through this example and then we'll talk about the key point and make sure that it's clear. So it says, given that A is this vector, find the vector B such that this thing is true. Okay, so let's see. So vector A is 5, negative 4, 2. Remember I mentioned you guys I really like column vectors, so I'm just going to go straight to this. So this minus, now the B vector. I'm going to go and just give the b vector a name. Let's just call these components x, y, and z, just so that we can sort of like see more plainly what this is. So they're saying that this should be equal to 3j. Now, how do I write 3j in column vector form? Hopefully you guys recognize this just means 0, 3, 0. Okay, so what this problem is saying is it's saying, hey, you've got this vector A, there's something you could subtract off of it so that the result would be 0, 3, 0. And what I want to share with you is, remember this key point, right? When you're working with or solving a vector equation, you can consider a separate equation for each of the components, right? So what I mean by that is, let's look at the x components. The x components of this tell me that 5 minus whatever x is has to be 0. Okay, I got that because I looked at the x components. Okay, but I also know that for this equation to be true, the y components have to line up. All of these things have to match one another. So negative 4 minus y is going to have to be 3. And finally, the z components are also going to have to match up. 2 minus z is going to have to be 0. And now, I guess what I have is I have 3 equations and 3 unknowns. I guess this is a system of equations, but it's really easy because they're not really related to one another. If I just move this x over, I find that the x coordinate has to be 5. Let's see, if I move the 4 over, I'm going to wind up with negative y equals 7. So that means y has to be a negative 7. And finally, over here, if I just move the z over, I'll wind up with z is 2. Great, so they said find the vector b. All right, so the vector b would have to be 5, negative 7, 2. And that's the answer to my question. So the idea here is when you've got a vector equation, when you've got, one vector plus another vector equals another vector, what I want you to do is I want you to realize, hey, I can really just take this thing, I can just take this thing and I can split this into 3 separate component equations and then solve each of those, maybe using systems, maybe just doing an easy thing like this. So I hope that made sense. We're going to go through several more examples of this, and then we're even going to see how this connects to parallel vectors sort of right at the end of the video. So this next example is fairly straightforward. I'd encourage you to pause the video and try it on your own. If you'd like, sort of take your first step and then watch what my first step is and make sure that you're on the right track, but I think you can get through this one. So they give us these vectors and they give us a relationship that sort of relates these things, and they're asking me to find the value of t. So I know at the end of the problem, t is what I'm supposed to find. So I'm going to take this and I'm going to sort of substitute in these things. So I have negative 241, that plus t times b, 105. That's going to have to equal c, which is negative 5, 4, negative 14. So I have this thing, and now they want me to find a value of t. Well, I guess what I'm thinking is that this t could really get distributed to all of these things, right? If I distributed that, I'd have negative 241 plus t 0, 5t, and this would still be equal to negative 5, 4, negative 14. Okay, so now I have this vector equation. Remember what we learned on the previous example. When you've got a vector equation, you can set the components equal to one another. You can make individual equations for them. So the x components are going to get me negative 2 plus t equals negative 5. Now, it might be tempting to just stop right here and solve for t, but I'm going to need to talk in a moment about why we can't do that. And let's keep going. The y components here would tell me that 4 plus 0 equals 4. And the z components would tell me that 1 plus 5t equals negative 14. Now, let's go back to this first one, right? If I'm looking at this one and I solve it, I'm going to wind up getting that t is, if I just add this 2 over, t is negative 3. Okay, so I seem to have found the value of t. But here's the thing. All I've actually shown at this point is I've shown that t allows the x components to match up. I'm not positive if the y components and the z components are going to match up. It might be that there is no t so that this works, and that happens sometimes. So we really need to check the other components to make sure that they're also going to be okay. So now let's look at the y component. Okay, so what this means is, it means that t has nothing to do with whether or not the y's match up. In other words, the y's are always going to match up. So y just sort of agrees with it, whatever's happening around it. So we're fine with y. Let's check the z component. For the z component, I can take this thing and there's actually two ways to do it. Either you can take this value of t and plug it in and make sure it works, or you can just solve for t and make sure it matches. I'm going to solve for t. So 5t equals negative 15. So when I divide, I get t is negative 3. Hey, wonderful. The values of t that we got all match one another. And so now we can say that confidently t equals negative 3 is the value of t that allows this thing to be true. Okay, so again, the thing that allowed us to solve this was sort of this idea that we took our vector equation and we broke it into 3 component equations and then solved those individual ones using the knowledge of algebra that we already have. So in this next example, you're again given 3 vectors and being asked to show now that there's no m such that this equation works. And I alluded to this in the previous problem that it's possible that you have a vector equation that can't work out, where it's not possible for the components to line up in the right way. So I want us to get a chance to see that here. So this should be really similar to the last problem. I'd encourage you to try it on your own. So now let's go through and see how you did. So I'm going to take these vectors and I'm going to sort of write this equation out using them. So A is 8, 2, 3. For the next part, we know that we're just going to want to distribute this m in. So if you're interested, you can sort of skip a step here and just multiply that m in, get negative m, 5m, and 6m. And then over here, you could do the same thing. We know that this 3 is going to get multiplied into all of the things that are in the c vector. So we could write this down as 6, 12, 21. If you didn't do that, if you wrote that as 2 separate steps, it's fine. Just wanted to show that you can do that. Next, now that we've sort of got this vector equation, I can set the components equal to one another. I'm going to have 8 minus m equals 6. And then my y coordinates tell me that 2 plus 5m equals 12. And finally, my z coordinates tell me that 3 plus 6m is going to have to be 21. Okay? Now I can go through and I can solve each of these things, but I do want to say something. If you haven't done this problem for yourself, if you're following along, I at least want you to sort of think for yourself, what do you expect to see happen here? If there isn't supposed to be a value of m such that this works, what do you think is going to happen when we solve these 3 equations? Hopefully what we expect is that we're not going to see the same value of m. We'll see like different values of m. So let's sort of keep that in mind as we move forward and watch what happens. So for this first one, if I subtract the 8 over, I'll have negative m equals negative 2, so that means that m has to be 2. Now I want us to think very specifically about what we've shown at this point. And I know I'm making a big deal out of an easy problem, but this is going to build into something really important later, like a few lessons down the line. What exactly this means is that it means that when m is 2, the x components are matching. Okay, so 2 is the only value of m where the x components are equal. Now let's go on and look at the y components. Right, when I move on to the y components, I can subtract the 2 over, and I get 5m equals 10. That means that m is 2. Okay, so I can actually go back and I can update this statement now. Right, 2 is the only value of m where the x and y components are equal. Okay, so now finally let's look at our z component. When I subtract this 3 over, I'm going to get 6m is 18, and it looks like in order to get the z components to match up, m has to be 3. So what that means is, it means that it's not possible. There is no value of m where I can make all of these components match up, which means there's no value of m so that this equation can work out. Now, I want to be clear. You don't need to write out the sentence for each one of these things on every one of these problems that you do, but I do want to point out that if you're writing an extended essay about vectors, or if you choose to do an IA about vectors, or if you're ever writing about vectors in a formal setting at all, it's really important to be able to express ideas like this. And like I said, at some point down the line, we're gonna get to a skill, and I'll tell you what it is, the intersection of vector lines, where this skill and being able to understand exactly what's happening as these different components match up, it's going to be something that we want to be really good at. So now that we've got some of these basic skills down, we're going to move on and talk about how this connects with the concept of parallel vectors. Unsurprisingly, we're going to start with some vocabulary. Okay, so first is the word equal. which is sort of funny, but I just want to make sure we're clear. So two vectors are equal if they have the same magnitude and direction. So, like graphically, that would mean that you'd have a vector like this, and then another vector that's the same direction and the exact same length. Okay? In terms of their components, it means that all of their components will be equal. Okay, so if two vectors are going to be equal, you need all their components to be exactly equal to one another. That's kind of what we were showing in the last two examples. In the first of those two, we showed that we could get those two vector sides of the equation to be equal, and in the second one, we couldn't get that to happen. Okay, now that's for vectors being equal, right? We could also talk about vectors being parallel. Okay, two vectors are going to be parallel if they're in the same direction or in the exact opposite direction. So if you have a vector like this, I suppose I already drew them up here, right? These two vectors up here are parallel, right? They also happen to have the same length. I could have two vectors that are the same direction but have different lengths. That would make them parallel. You can also have vectors that are like this, okay, where it's kind of the same direction, but they're kind of in exact opposite directions. These are parallel vectors, but often or sometimes we use the word anti-parallel to express that, because it's sort of like they're in the same line direction, but they're actually literally going the exact opposite direction. So you can see how it's like there's a very specific type of parallel that is they're anti-parallel to one another. So here's how this connects to vector algebra. Here's how this connects to all of this equation work that we've been doing, okay? Two vectors can only be parallel if one of them is a scalar multiple of the other. In other words, if these two vectors are going to be parallel to one another, you basically have to have just multiplied one of them by a scalar. And so we can express that algebraically. A and B can only be parallel to one another if one of the vectors is equal to some scalar multiple of the other. By the way, we generally say that t can't be 0, because otherwise one of those vectors is 0, and we don't really want to talk about a vector being parallel to the 0 vector. So what we're going to be doing in our next couple of examples is not showing that two vectors are actually equal to one another, but showing that one of them is equal to a multiple of the other one. We're going to be showing that they're parallel to one another. So let's take a look at this example. Given the vectors a, b, and c that are stated up there, part A says find the values of p and q. Now, p and q are like components of c. So find the values of p and q so that the c vector will be parallel to a. Okay, so if I want c to be parallel to a, remember what we learned on the previous slide, right? For c to be parallel to a, c is going to have to be some actually, maybe we don't want to use k because they're going to bring it up later. C has to be some scalar multiple of a. By the way, I could totally also have written this as that a has to be some scalar multiple of c. It doesn't really matter very much. I chose to put the m, the scalar, with a just because that one already had all numbers in it. So now that I have this, I'm going to say, all right, my c vector, 2pq, has to be equal to m times my a vector. So that would be m, 2m, and 7m. Okay? All right. Now you may be a little bit worried here because there's just like letters everywhere, right? But remember, for as much as there's 1, 2, 3, 4, 5 different letters here, c and a were just referring to vectors. So those are gone. This is really just 3 unknowns that are left. And it's actually 3 unknowns and 3 equations, right? I can set this up as a system and say that, well, 2 would have to be equal to m, and p would have to be equal to 2m, and q would have to be equal to 7m. And we were being asked to find p and q. Well, fortunately, this is a really, really easy system, right? We can already see that m is 2, so now we just plug that in. When I plug that in, I'm going to find out that p has to be 4. And when I plug this m value in over here, I'm going to find that q has to be 14. And so there it is. I found the values of p and q that are going to allow a to be parallel to c. Okay. And if you'd like to see that really plainly, you can actually write it out really quickly. I just want to show you guys this really quickly. So this means that the a vector would be 1, 2, 7, and the c vector would be 2, 4, 14. And when you look at it like this, you can really plainly see, oh yeah, this vector is literally, oops, I forgot the equal sign. This C vector is literally just twice this one, right? We can see that the C vector is just 2 times the A vector. And that's what lets us sort of really plainly see that these two vectors are indeed parallel to one another. Now, part B is slightly more challenging. I'd really encourage you guys all to try it on your own, sort of see where you can get. As always, if you're feeling uncomfortable with that, try the first step and then check in with me and see if you've got a good start to it. So they want me to find the value of the scalar k, which is right there, find the value of that thing so that this vector is parallel to this. Now, sometimes students get bogged down in like they see a plus kb is parallel to, and they go, wait, do you mean a or do you mean b? Like, what has to be parallel? Remember, when I take a and add it to kb, that is a vector, right? So I want you to show that that thing's parallel to the other vector. So first I'm going to sort of write down this expression. A is 127 plus kb. I'm going to distribute the k into this b vector. So this is going to be negative 3k, and then the y component will be 4k, and the z component will be 2k. So I need that to be parallel to this vector. All right, if I want that to be parallel to that vector, how do I set up an equation for this? Well, I would need this to be equal to some scalar multiple of the vector I want it to be parallel to. Now, I don't want to use k because k is already in the problem. I don't really want to use m because m was already used back up here. So let's just use a new scalar. Maybe we use, n hasn't been used yet. I'm going to use n. If you used, a or b could work. Those are a little bit weird because you've got these vectors here. Anyway, we've got this thing. Let's see how we can solve this, okay? So let's see here. My x components are going to come together and tell me that 1 minus 3k has to be 0. Well, that's going to be really convenient. My y components are going to come together and tell me that 2 plus 4k has to be 10n. And finally, my z components are going to come together and tell me that 7 plus 2k equals 23n. I now have a system of 3 equations with 2 unknowns, and I want to go back and I want to go through and solve these and make sure that it's all going to work out. So I'm going to solve these things now. Looks like in this first equation, we're going to find that k is 1/3. So that value of 1/3 sort of needs to follow through and function for all of these others. So substituting into this middle equation, we'll get 2 plus 4/3 is 10n. Let's see here. So if I make this thing 6/3, I'll wind up with 10/3 equals 10n. And so when I divide by 10, I'll get that n has to be 1/3. And then for this last one, you can either plug the k in and solve for n, or you can plug the k value in and the n value in and like show that it works. I mean, hopefully it's going to work. Let's see here. So 7 plus, and my k was 1/3 here. So 7 plus 2/3 equals question mark 23 times 1/3. Let's see here. This 7 would be 21/3. So if I put those together, I get 23/3. That equals 23/3. So yay! So this thing all worked out, right? And now we actually need to scroll back up and take a look. Wait, what was this question even asking for again? It said find the value of the scalar k such that a plus kb is parallel to that vector. We needed to find the value of k, and we found it. That value of k is 1/3. Okay, k is the thing that allows these two vectors to be equal. When k is 1/3, the x components match up. And when k is 1/3, it forces n to be 1/3, and doing that causes the y and z components to match up. I know this is a really long example, but I wanted to make sure that you guys really saw all the pieces that went into showing that two vectors are parallel to one another. All right, I've got one final example here of us working through a fairly complicated example of showing that vectors can be parallel. So I would encourage you again, pause the video, try this one on your own, see what you get. One of the first things I'm going to do is stop writing these things in IJK notation. It's just too many letters floating around. So let's see here. given those two vectors, find the values of the scalars m and n, so they want me to find two of them this time, such that ma plus b is parallel to this vector. Okay, we can do that. So ma means 2m, m, and negative m. And if you didn't see where that came from, it's basically m times the a vector, which was 2, 1, negative 1, and then I distributed that m into those things. So that plus the b vector, now my b vector is n, 2n, and negative 8. And I got that by grabbing the coefficients in front of I, j, and k. It says that this is going to need to be parallel to this thing. All right, so it's going to need to be a scalar multiple of 1, negative 2, negative 4. Now, I want to make sure that's really clear to you. So if you need to, pause the video, think about that. If it's still really unclear to you, write a question about that inside your notes. Reach out to a friend, send me a message and ask me about it. I really, really want to make sure we're comfy with that. So now that I've done this, I'm going to do the same thing I've done in all the others of these. When we have a vector equation, we break it down into its components. The x components tell us that 2m plus n has to be equal to 1. The y components tell me that m plus 2n has to equal... Oh, sorry, I just realized back here that shouldn't have been 1, this should have been k. For the y components, m plus 2n should be equal to negative 2k. And for the z components, negative m minus 8 should equal negative 4k. Now, it's been a little while since we've done these, but what we have here is we have a system of equations with 3 equations and 3 unknowns. And our strategy for solving those was to eliminate the same variable twice. So you'll notice that at the end down here, n has already been eliminated. So what I want to do next is I just want to eliminate n again. So I want to use these 2 equations to eliminate n. I'm going to do that by taking this equation and putting it here, multiplied by negative 2 so that the n's will cancel out. So when I do that, I'll get negative 4m minus 2n equals negative 2k. So when I add these up, like we said, the n's drop out, I get negative 3m equals negative 4k. All right, so now what I have is I have 2 equations that only have 2 unknowns. This is just like normal system of equations like we've always solved. It looks like the elimination on this one's actually also going to be pretty easy. If I just put this one here and multiply it by negative 1, I can get the k's to drop out. So this is going to give me 3m equals positive 4k. Those drop out. I'll get 2m minus 8 equals 0. That means 2m is 8, which means that m has to be 4. So we found one of our values. Now I can take that and plug it back in here. I'm going to start using a different color just to keep things a little bit different. When I put this in, I'm going to get negative 3 times 4 equals negative 4k. Negative 12 equals negative 4k, which means that k has to be 3. That wasn't one of my answers, but it's one of the other variables that I'm working with. So I can now take the k value and put it in, and I can take the m value that I got and put it in over here. Doing all of that will get me 2 times 4 plus n equals 3. 8 plus n equals 3, which means that n has to be negative 5. And so what we found here, the question was asking us what were the values of m and n that allowed these to be parallel. M being 4 and n being negative 5 caused these things to be parallel to one another. I know this video is already really long, but I did want to point one thing out. You guys often hear me talking about the importance of checking your answer. So if you've done all this work and you want to make sure that you're right about it, something that you can do is you can put these back in and sort of show that this actually worked, right? If m was 4, it would mean that this ma vector would be 8, 4, negative 4. And the b vector, well, let's see here, we knew that n was negative 5, so the b vector would be negative 5, that's that, minus 10, that's from that, minus 8. When I add those two things together, I'm going to get 3, negative 6, negative 12. We were supposed to show that this thing was parallel to this vector, 1, 2, negative 2, negative 4. And we can see it really clearly. The connection here is that it's 3 times longer. Like you can really plainly see that if you multiply this vector by 3, you're going to get that. So it's really nice to get to the end of one of these problems that we put a lot of energy and a lot of work into and find, hey, look at that. Like everything really did work out well. So this is vector algebra. These are parallel vectors. These are some really, really important base skills that we're going to sort of practice and make sure we're good at so that we've got them when we move on to harder things. As always, if you've got questions, please let me know. Best of luck as you work through the assignment.